Hello and welcome to Void Electronics. In today's video I would like to talk about the spectrum analyzer. More specifically, I want to show you what a spectrum analyzer is, what are its main settings, how it works, and even how it relates to one of the most important mathematical discoveries of the 19th century. So let's get started. In electronics we often work with 2D graphs, and these 2D graphs represent something with respect to something else. So whatever it is that we're trying to represent is on the vertical axis and our reference variable is on the horizontal axis. Let's see how this applies to the spectrum analyzer. The spectrum analyzer is a piece of test equipment that represents amplitude with respect to frequency. So the frequency is on the horizontal axis and the amplitude is on the vertical axis. This means that if we apply a sine wave at its input, instead of getting the sine wave function that we're all familiar with, we get a peak. And this peak is at the frequency that we are inputting, of course. Now, signals are rarely purely sinusoidal, so if we change the waveform, we get a completely different result on the spectrum analyzer. As you can see, in the case of the square wave here, we kind of have multiple frequencies happening at the same time. So the signal that we're applying here contains multiple frequencies, and these are all called harmonics. The harmonics are nothing else than integer multiples of our initial frequency, which is called the fundamental. So here we apply a square wave at 5 kHz, and you can see the fundamental right here, which is 5 kHz. But we also see the second harmonic, which happens at twice that frequency, which is 10 kHz. The third harmonic, which happens at 15 kHz, and so on. In theory, a square wave should have an infinite number of odd harmonics. But since our signal is not ideal and the spectrum analyzer can only have so much bandwidth, we can see a few of them. And we can only see so many harmonics due to the limited bandwidth of this spectrum analyzer. Not that the signal will go to infinity anyway. If you know a thing or two about electronics, you're probably used to seeing a sine wave like so, like we usually see it on the oscilloscope. And now, when we're introducing the spectrum analyzer, you can see that the sine wave can look completely different. It looks just like a peak here. And if that's not strange enough, if we change the waveform to a square wave, then we get multiple frequencies at the same time. So how on earth is it even possible that this and this are basically the same thing? Well, this has to do with a discovery that revolutionized mathematics in the 19th century, and that is the Fourier Transform. Basically, Joseph Fourier demonstrated that any periodic function can be broken down into a sum of sines and cosines of different amplitudes and frequencies. And the mathematical process of doing so is called the Fourier Transform. Not only that, but this also works in reverse. So any periodic function can be made up of sines and cosines of different amplitudes and frequencies, and this is called the inverse Fourier transform. The direct application of this mathematical concept is the spectrum analyzer. And if this doesn't convince you, let me show you that the synthesis part can also be easily demonstrated in LT-Spice. So if we connect some sine wave sources in series and we set the amplitudes and the frequencies just right, we can synthesize this 5 kHz square wave using only sinusoidal signals. And as you can see, the more terms we have or the more sources we have, the closer we are to a perfect square wave. But how can we get from this graph, which is a time domain graph, to something like this, which is a frequency domain graph? Well, imagine that we can analyze our signal using a very narrow filter. And then we sweep that filter in frequency and measure the amplitude that we get at the output. And we do this for every single frequency, of course. Well, this kind of gives us a frequency domain graph like we see here on the spectrum analyzer. And I know, it sounds like you need a really exotic piece of test equipment to do this, right? Well, not really. That's actually what the radio does. If you think about it, the radio already has a narrowband filter that's tunable using this frequency knob, right? So that means that we can sort of play with the radio and get our own frequency domain graph of the FM broadcast band. So let's give it a try. Let's sweep it across the band and see what we get and trace our own graph. So far we have pretty much nothing here, just noise, not much here. Okay, here we have a strong station. So we have a peak here. Let's move on. Maybe just some noise. Another strong station here. A weak station here. Another station here that's relatively weak. This one is very strong. This one's also pretty strong. Another strong one here. This one's very weak, but is there. And here we have another one that's pretty strong, and you get the point. Here it is. We have our own handmade frequency domain graph of the broadcast band. Now this is exactly what the spectrum analyzer does automatically. With this in mind, let's go back to our spectrum analyzer and see what the main settings do. First of all, let's see how we can safely apply a signal to our spectrum analyzer. No matter what spectrum analyzer you have, it always has a limit for the maximum input level that you can apply to it. So make sure to read the manual and never ever exceed that limit. So when working with radio frequency spectrum analyzer, that level is usually a power expressed in decibels, or otherwise for low frequency stuff it could be a simple voltage in volts, like a peak voltage or something like that. And also, if you're working with radio frequency equipment, make sure that this input is properly terminated, usually into 50 ohms. So either the spectrum analyzer can do this, or you have to use an external terminator like this one and a T adapter, or maybe a through terminator like this one. And then with this in mind, we can move on to the settings. And one of the most important settings is the input range, which is basically the sensitivity of the instrument. Once again, if you know you're applying a high power signal, don't set this to maximum or you can blow up the front end. So just set it to minimum sensitivity and work from there, I guess. In this case, you can adjust it from the input menu, select the input range, and you can manually adjust it like this. It says that auto range is off, which is okay. And if we set it to a really low value, as you can see, we can overload the front end and get extra harmonics that are not part of our signal, because the front end distorts. So you have to set it to a reasonable level like this one, or you can simply press auto range and the instrument will set the range for you. And as you can see, this looks good now. What you can also do here is you can auto scale it, or you can set the scale manually so that you get a reasonable range between the minimum amplitude and the maximum amplitude that you see here, so that the signal looks right, so that it has the right, let's say, height on the screen or something like that. This can be also set manually by pressing the scale menu, and as you can see, you can set here the bottom reference, which is the lower level, or the top reference, which is the upper level, but in this case they just move in sync, and that's because you have a fixed amount of decibels per division here, which is something that you can also set. So by increasing this number, as you can see, our peak gets really small. We can also decrease it, we can also move the bottom reference and so on, but now, as you can see, the dB per division is so low that our signal doesn't fit anymore. So we can either adjust it manually or just do auto scale, and it's adjusted automatically. And that's about it when it comes to the vertical scale, I guess. So to sum things up, make sure that the input signal doesn't exceed the maximum supported by this instrument. Start with a large range and work from there. and then you have to set the range so that the front end doesn't distort, and then you can also set the scale in dB per division so that your signal looks basically as high as you wanted it to be. And then, just like you would on the oscilloscope, you can also offset the signal up and down, and this is what the top reference and bottom reference settings are for. Now let's move on to the horizontal axis settings. First of all, we can set the frequency span. The frequency span is of course the difference between the maximum frequency that we can see and the minimum frequency that we can see. This can be adjusted in the frequency menu of this spectrum analyzer, and in this case, since this is a very low frequency spectrum analyzer, the maximum is 100 kHz. Let's see why you would want to adjust this in the first place. Well, first of all, in some cases, if we use the spectrum analyzer at full span, you may not be able to see certain detail in your signal. And such an example would be if you have a signal that's amplitude modulated, for example. So let's turn on amplitude modulation here. So now we have a 50 kHz sine wave that's modulated by a 1 kHz sine wave. And if you look at the spectrum analyzer, it basically looks like a single peak, so you don't really see what's going on here. And the best solution to this is to just reduce the span in our area of interest until we can see the sideband signals. And as you can see, we reduced our span to just 6.25 kHz, and now you can clearly see the sideband signals. And by selecting the marker, you can even measure the frequency of these sideband signals to see if they are right or not. And as you can see, they're bang on. This one is at 49 kHz and the upper sideband signal is at 51 kHz. So this is what the span can do for you. Another important setting is the center frequency. So by selecting it, you can obviously offset your center frequency in case you want to look at something else. And you can go both ways, of course, and this spectrum analyzer also allows you to set it in a different way, basically by setting the start frequency instead of the center frequency. The start frequency is of course the frequency that you have at the left of your graph. You can also adjust it, and since the span is fixed, it just moves together with the center frequency, which is I don't know, it is a bit strange and counterintuitive, but this is how this instrument works, at least. And there is a trick to recentering it if you want. You can select the marker, select the carrier frequency, and then you can press center, and everything's centered once again. Another important setting of the horizontal axis is the resolution bandwidth. The resolution bandwidth is basically how narrow the filter that analyzes the signal is. And in this case, this is a digital instrument, so it doesn't really have an analog filter that sweeps from the start frequency all the way to the stop frequency, because this is done using digital signal processing. However, this instrument does have an equivalent resolution bandwidth, and that resolution bandwidth is the span divided by 400. That's because I think this instrument uses 400 FFT bins, so it has an equivalent resolution bandwidth of our span divided by 400. On other instruments, especially analog instruments, this is something that you can set using a knob. In this case, this is basically a fixed ratio from our span. And now we also have another interesting parameter to play with, at least in the analog world, which is the video bandwidth. Now the video bandwidth is basically a low-pass filter after the radio frequency detector, and its purpose is to reduce the noise and the variation that you see on the graph. Now this instrument being digital, it doesn't really have that, but it has a digital equivalent to it, in my opinion, which is the averaging function. So we can go to average here. We can select the number of averages that we want. Let's say we want 10 averages, and then we can enable it. And by enabling the averaging, as you can see, the noise here got lower. I mean, it doesn't really lower the noise floor of the instrument, because that's pretty much impossible, but at least we have less variation and it doesn't look as annoying as without it. It smooths the waveform, if you will. Another set of important settings is the way you configure the axes. That's because on a spectrum analyzer, the graph that you have on the screen is usually a double log graph, meaning that both the x-axis and the y-axis are logarithmic. This is an interesting trick that we usually do in RF because this allows us to see detail in both very low frequencies and very high frequencies. And this applies of course to the y-axis, where this allows us to see detail at very low amplitudes and also have a signal that is much higher in amplitude visible on the same screen, as you can see right here. So to demonstrate this really quickly, we can change the settings just a bit. Currently what this does is that it has a logarithmic y-axis and a linear x-axis. So first of all, let's play with the y-axis and make it linear to see what a difference it makes in the way this signal looks. So notice the noise floor here, which is clearly visible, and also our useful signal, which is also visible here. We have a peak. Let's see how it changes when we change the axis to a linear one. So to do this, we have to go to the measure menu, select display, and then linear magnitude. And as you can see, the noise floor is gone. So did we magically remove all the noise? Well, not really. But now, since this plot is linear, you don't see the noise anymore, because here the noise has a really low amplitude with respect to our useful signal. So we only get a clean peak. And as you can see, the unit displayed now is in volts instead of dB. In some cases this might be useful, but most of the time this is a logarithmic scale. So you need to go back to the logarithmic magnitude option here. This brings back the noise floor, and this brings back the dB measurement right here. And you can do the same thing with the horizontal axis. To do this, we have to go to scale and select log here. And as you can see, now it looks completely different because the x-axis is now logarithmic. Once again, this is very useful, especially in RF. And this basically means that you don't have a constant distance between two divisions anymore. As you can see, the divisions right here are 10 kilohertz apart. So this is 20, 30, 40, 50, and so on. However, if we look at this group of divisions, they are at a different distance from one another. For example, this one is at 2 kilohertz, this one is at 3 kilohertz, 4, 5, and so on. So this is what a logarithmic scale does. And by the way, you can also change the unit of the Y variable here that corresponds to the marker by selecting the measure menu, units, and then you can change it to volts peak, volts RMS, dBV, and dB VRMS. By now you probably figured out the main use cases of a spectrum analyzer, but let's just highlight some of them anyway. First of all, a spectrum analyzer can be used for RF transmitter testing. So it's very important when running a transmitter that the signal is clean before putting it into an antenna, because the transmitter needs to comply with local regulations, and you have to make sure that the transmitter doesn't interfere with anything else. So if your signal looks like this, it's probably clean enough to be put into an antenna. However, if you have some sort of horrible distortion somewhere in the signal path, your signal could look something like this, and this means that you have lots of harmonics to take care of and to get rid of before putting the signal into an antenna in a safe manner. Similarly, a spectrum analyzer can also be used for checking a modulator. So you can check the main modulation parameters like modulation depth for AM or frequency deviation for FM, and this can be easily demonstrated. For example, here's an AM signal, and you can clearly see the modulation here, and you can also switch the generator to FM, and in this case here's what an FM signal looks like. This can be characterized by the spectrum analyzer once again to make sure that the modulator works right before connecting it to a transmitter and an antenna. The spectrum analyzer can also be used for EMC compliance. I know, it sounds like we are repeating the previous topic, however that's not the case. Because don't forget that there is a class of devices called unintended radiators, meaning that some devices emit radio frequency noise as a side effect of their operation. And I can also demonstrate this really easily. All I have here is a scope probe that's shorted out and is connected to the spectrum analyzer, and this loop of wire acts like an antenna. Watch what happens when I put it close to my desk lamp. As you can see, we have some spectral components here at around 30 kHz, 60 kHz, so this is the second harmonic, and also at 90 kHz. So this means that this desk lamp puts out some radio frequency noise. And we know it comes from the desk lamp because we can turn it off and the signal is gone. Another important parameter that we can read from a spectrum analyzer is the signal to noise ratio. In this case, by moving the marker on top of our useful signal, we can see that the signal sits at around -15 dB. And then we can also move the marker aside to measure the noise floor, which sits at around -90 dB, and this gives us a signal to noise ratio of around 75 dB. A really good value in this case. And finally, the spectrum analyzer is really useful for characterizing distortion and measuring the THD. So if you want to ruin the day of your favorite friend who's an audiophile obsessed with vacuum tubes, just measure the THD of their amplifier. In order to demonstrate this, I decided to set up an experiment that consists of a signal generator, a guitar amplifier and a guitar pedal, which is actually a fuzz pedal. Now the fuzz pedal is supposed to add distortion on purpose in order to change the tone of the instrument, so it's a really useful tool for seeing how the spectrum changes when we add distortion. Let's enable the signal generator. So far we have a clean sine wave at 1 kHz. Nothing spectacular here, we only see a peak here and a spurious signal, but let's ignore it for a while. And now let's enable the distortion and see what we get. So with the fuzz pedal enabled, we can see lots and lots of harmonics here. And this is characteristic of a system that has tons of distortion, which is exactly what the pedal is supposed to do. Now what we can do in order to characterize how much distortion we have is to measure the THD. So let's reconfigure the spectrum analyzer for this. In order to do this, we have to start it once again, go to Analyze, Harmonic, and then we have to set up a few parameters here. For example, we have to set the fundamental, which is correct, it's 1 kHz. Then we need to think about the number of harmonics that we want to analyze. Let's say we want to look at 10 harmonics. And now we have a THD measurement here on the screen, and our THD is around 0.1% or something like that. Maybe we can pause it to have a quick look. So I think this is an acceptable amount of distortion. Let's enable the pedal and see what we get. So now, as you can see, the distortion is much higher, it's at around 50%. And by overdriving the pedal even more, we can get even more distortion if that's what we wanted. So let's increase the signal level. And as you can see, the more input we give it, the higher the distortion gets. So we got to a THD of around 80%. And the final step in mastering the spectrum analyzer is understanding how it works. For this, I highly recommend reading this document called Real-Time Spectrum Analyzer Fundamentals by Tektronix, where they go into lots of detail about how a spectrum analyzer works. So let's have a quick look at the block diagram that describes an old school spectrum analyzer, an analog one. And here we can see lots of blocks, maybe an unexpected amount of blocks actually. Why do we have so many blocks here? Well, we have them because people realize that it's really hard to make a tunable filter that can also be swept, especially with old school analog electronics. So instead of relying on complicated mechanical stuff in order to tune a filter and also sweep it, people decided that it's a lot easier to have a spectrum analyzer that is only sensitive to one frequency basically, and then using a mixer and a swept local oscillator, you can down convert the input to that frequency that the spectrum analyzer is sensitive to, and this way you get a spectrum analyzer and the effect of a swept filter without actually having a swept filter, if that makes sense. So an old school analog spectrum analyzer consisted of an input attenuator, a low pass filter at the input, a mixer and a swept local oscillator, and after this we have the resolution bandwidth filter, which I explained at the beginning of this video. We have basically an RF detector, which can be a diode. Then we have a video bandwidth filter for smoothing out the plot. And then we have a display where the y-axis is basically the output of the envelope detector and the x-axis is the output of the sweep generator that sweeps the local oscillator and sweeps the trace on the CRT. Of course, this is mostly history by now, and the more modern architecture relies on some digital electronics and digital signal processing. So a more modern architecture can look something like this. Once again, you have an input attenuator, a local oscillator and a mixer that down converts the frequency at the input to an intermediate frequency. However, after down conversion, this intermediate frequency is sampled by an ADC, and then the spectrum can be obtained using digital signal processing and applying the fast Fourier transform on the samples. In some cases, the ADC is fast enough to directly sample the input, which is the case of the spectrum analyzer presented in this video, so you don't need the RF down converter stage anymore. Of course, this is just the tip of the iceberg, so in order to keep this video relatively short, I highly recommend reading this document on your own. It will be linked in the description of this video. So that's it. If you like this video, please give it a thumbs up, and if you're interested in more content related to electronics and programming, please subscribe to this channel because there is more content like this on the way. Also, don't forget that you can support this community by giving me a super thanks on YouTube or by joining my channel using a paid monthly subscription. That's all for now. Bye.